Hello friends, welcome to H lesson, and today we are starting to do what many of you have been waiting for throughout the course. We are starting to create our own token on the Ton blockchain. And today we will write it. However, before that we need to cover another important topic. I mean how to create unlimited data structure on Ton. If you recall our previous lessons, we discussed with you that you can store unlimited data structures within one smart contract. We looked at this on the example of a map when we added new elements and the commission for adding a new element kept growing, and this indicated that this is not an unlimited data structure. Sooner or later we will lose the ability to write something there. So today we will study an important pattern when developing smart contracts on Ton, namely the actor model. And we will look at this on a simpler example of TodoList. Okay, let's start with a little theory. I want to schematically show the difference between how we would create a to-do list, for example, on the Ethereum blockchain, and how we will do this on the Ton blockchain. We have one smart contract called TodoList, and we write our data structure into this smart contract. So we have some array with our items here, and if we want to add a new to-do to our to-do list, we send a transaction to our smart contract, and then our contract extends and a new element is added. Okay, everything is clear here. Now let's see how this will work on the Ton blockchain. First of all, we will not have one entity or one smart contract here, but we have many of them. The first and main smart contract will be called to-do parent. As you can guess, this is the main smart contract, and new items create through it. That is, each to-do will be created through to-do parent, and each to-do will be separate smart contract. And now if you want to create a new child, we send a transaction to our contract, as in the first case, and it creates a new child. In this case, we get an unlimited structure. There can be billions of such contracts. Conceptually, these approaches can be compared to monolith and microservices. Our first smart contract can be represented as monolith, as one large service with large storage that can contain billions of records, and all action and all logic occur only within this smart contract. And the approach we use in Ton is similar to microservices, because each smart contract is like a small service. Okay, let's now switch to the code and implement this scheme in our project. I have already created the first contract. Let's create the second one. Our to-do parent will be the contract for this. I import the library we are already familiar with and create one more field, num to-dos. With this variable, we will know how many to-do childs exist in our system. From the to-do child contract side, we will have fields like parent, sequence number in our structure, task, and status. The init method will accept two arguments, the parent and its sequence number. Next, we will write a method in our to-do parent contract, a method for creating a new to-do child. We will have a message new to-do. I haven't written it yet, but I'll write it a bit later. Here, first of all, we increase the counter of our num to-dos and then get init of the to-do child contract. And as the first argument, we pass the address of our parent. For this, here we will use the myAddress method, and secondly, we will pass num to-dos. Good. Before forming the message, let's write our new to-do message first. In this project, we will have several messages that will be used in different places. So let's create a separate file for this and bring all the messages there. Our first message will be new to-do. and here will be a single field, the task field of the string type. Okay, now I need to import our message here. Further, when we form a message to send TodoChild contract, we need to understand what message we want our TodoParent to send to the TodoChild contract, because here we will accept it. I'll immediately name it internal set task. By the word internal, I note this is a message that is forwarded only between smart contracts. This is not a message sent by a person. That is, from the client side, we will never send such a message. Let's write this logic before setting the task. We must check that our sender is the parent contract and assign the task field the value that comes to us from the message. Let's write this message in our messages file, and it will be similar to the previous one. Here we will have one task field, and of course we also need to import this into the TodoChild contract. Okay, we have already written the reception of the message, but we have not written its sending. Let's do this now. The address of TodoChild, as we already know, we can get from init using the contract address method. Then form the body. And as you understand, in this message, in addition to the fact that we send the internal set task message, we also deploy our new TodoChild contract, because we pass the code to it and pass the data to it. And we also pass some amount of Toncoins so that its contract can pay the commission for the network rent. But then the money that is left after execution this message, we need to return to our sender's address. For this, we use the reply method. In addition to replying, we will return the remaining money and also send a message. This message will act like a push notification. That is, our smart contracts can notify us when something that we expected has happened in the blockchain. This notification from smart contracts supported by wallets, and we will be able to see them in our notification that the smart contracts has performed what we expected. We will name this message new to-do response, and the only parameter will be the number of our to-do item. Okay, we have learned how to create new TodoChild. Now we need to complete them. We will also complete them through our main contract. For this, we will have a complete message. Let's immediately write it here. It will contain only the number of our to-do, and also add a check that only the owner can complete to-dos, and that such a to-do exists. When forming a message to complete a to-do, we'll use the simple principle. We'll create another message, which we will call internal complete, and in this message we will have only the access field, which will be the value of the sender's address. We do this so that when our TodoChild contract gets the message that the transaction is complete, we need to return the remaining money that was sent to complete all of these operations back to the sender's address. Okay, let's add this message to our message file. This time we are sending 0 Toncoin. Besides setIgnore, we will also add the send remaining value flag. Okay, and here we will write a method to accept this message. We will also check that the sender is a parent. Next, we change the completed flag to true and send the remaining Toncoins back to the sender's wallet. Well, that's it. Our structure is ready. Let's just write a couple more getters for each of them. And also write a getter for the TodoChild contract in which I will return the details of this to-do item. To return data, I'll use the to-do detail structure. Let's write it now. Here will be two fields, the task field of the string type and the status. Great, our smart contracts are ready. Let's write a small test to see if it works. I only need one test, so I deleted the second one. I'll call it should create to do. Of course, before writing the test, we need to check that everything is built correctly. Let's do this. We open the terminal and we see an error here that our to-do child contract cannot import messages. If you are watching this video recently after its release, you probably also catch this error. To solve it, we need to go to our package.json and update the blueprint framework to version 0.12. Let's do it, delete the node models and reinstall them. Repeat our build, to-do child, and this time everything went successfully. Let's do the same for our to-do parent. And here I see in advance that we also need to import the to-do child contract because we use it on line 16 to determine the state in it. New response not found. Looks like I forgot to write it. Yes, indeed. Let's write this message now. Here it makes sense to just pass the number of your to-do. We repeat. Our contracts has been compiled and now we can return to the test. To do this, first let's form a message of type new to do. Next, TypeScript will immediately suggest which fields we need to write. For task, let's write to do 1. Okay, and then let's immediately send our message to do parent using send, deployer, get sender. Deployer needs to be moved to the scope above. Okay, as a value let's pass 0.5 because 0.2 will be forwarded further to our to-do child and here they will stay. We will not transport them anywhere else and we pass our message as a third argument. Let's now get the instance of our to-do child contract. For this, we first get its address using the to-do address method in the to-do parent contract. And since we only have one to-do child, we pass its number, exactly 1. Okay, then we create a to-do child contract. We use our blockchain variable for this, open contract, then pass to-do child there, and here we form it not from init, but from the address. Well, we have access to our to-do child, and let's see what details it has. Yes, the expected response. We received our structure in which as a task we have the string to do 1 and at the moment completed is false. Let's now check that the completion will work. I write here the message complete and then I'll just send this message in the same way. Let's take another look at our details after that. And as we can see, everything went successfully. And on this principle, you can create any data structures. They can be of unlimited sizes, so this pattern in Tone is very used, and it is exactly that we will use to write our token now. Okay, it's time to write a token. I'll close all other files and start by creating a main contract. In Tone terminology, we will call the token Jetton. So let's name our main contract Jetton master. And right after that, I'll create a Jetton wallet. The first fields in our Jetton master will be the symbol field. It's like token's name for us. And the second field is total supply, which is the total number of all tokens that exist. Let me initialize ton as the symbol here, and the total supply will initially be known as the total quantity of all tokens. Let's say here that we'll have 500 jetons, and when we create our contract, all coins of this jeton will immediately be present at our deployer's address. We will also have a mint method here, which we will write a little later. It will take in the amount we want to mint and the wallet address to which we will be minting. Let's write this mint function. And here we need to understand this principle, how will the architecture of our token work. We have a master and we have a Jetton wallet contract. And as you understand, each user will have their own Jetton wallet contract, meaning their own wallet contract where the cryptocurrency will be located. In fact, if a user has several tokens, for example USDT or USDC tokens, it means that he has two separate Jetton wallet contracts. That is, there are as many wallet contracts associated with one user as there are types of tokens. In our case, when we send the mint method, we will be creating our Jetton wallet contract, which don't exist before. Now, to create it, we need to define its init. Of course, its first field will be parent. Every Jetton wallet should store the address of the Jetton master. The next field is owner. This will contain the wallet address of the user itself and the balance variable. This means that our init will have two arguments, parent and owner. And the balance will be 0 by default. Now let's write the first method for the Jetton wallet. We'll write a method for receiving cryptocurrency to its balance. A message for this we'll call internal add tokens, or let's just call it internal add. I'll write the message in the same file that we have already created. I will not create another one, and I will pass this message here. This message will contain an amount and an origin field. The origin will contain the address that sends this message. And okay, let's continue writing the mint method, and in a parallel write the receive method for the Jetton wallet. For this we create a variable init, take it from our Jetton wallet. As a parent we pass my address, and as a owner we use two arguments. Okay, we will also need to import our messages first, and secondly our Jetton wallet contract. Let's start writing this message. We are sending a message to the address of our Jetton wallet. For this, we can already calculate its address using the contract address method. As a body, we will use internal add message, where amount will be our argument and origin will be my address. As a value, let's pass 0.03. The mode will be send ignore, and also don't forget to pass the code and initial state. Good. We wrote the mint message. Now we need to write a receive method for accepting this message. First check we do here is that if our message origin equals to our parent, we should verify that sender is also a parent. But as you understand, we should be able to accept cryptocurrency not only from our Jetton master, but also from other Jetton wallets. Therefore, we need to make a check here that we can accept both Jetton master and contracts of exactly the same Jetton wallet. To do this, we will also use the require method and compare that our sender equals to the address we are about to calculate. We calculate it as follows. As a parent we pass self parent, and as an owner we pass the address from origin field. Okay, and we compare that our sender equals the contract address from the received init. It turns out that we have worked out such protection here that our Jetton wallet can accept internal add messages either from the master or from exactly the same wallets. They work by the same rules, have the same code from exactly the same Jetton wallet contracts with the same source code. This way, our internal add cannot be sent by anyone and our balance management functionality will remain safe. Therefore, now, after all checks, we can simply increase our balance by the specified amount. Okay, our wallet has learned to accept cryptocurrency, but we also want to be able to send our tokens further somewhere. For this, we will write another receive method. We will name the message transfer and let's define it in our file messages. Transfer will only accept amount and recipient's address. Okay, first of all, we need to check here that this message came from the owner of this wallet. The second check we will make is to ensure we have enough balance to send such an amount of coins. Now we just reduce our balance by the amount we sent in the message. And here is an interesting point in the transfer method. We will form an internal add message and send it to exactly the same as a smart contract, but let's first write it down and then discuss it again. In order to send our message, we need to know the address of the Jetton wallet to which we will be sending. At the moment, we know only the recipient's address, that is, we know the user's wallet, but we don't know his Jetton wallet. And let's calculate it. Now we form our message of the internal add type, then amount, and in the origin field we pass our owner, the field in which our usual wallet, not the Jetton wallet, but the one you see in your application in your phone. And here, friends, it's also an interesting point, because when we send a message, we don't know exactly if such Jetton wallet exists in the blockchain or not yet. It can be that we are sending Jetton to someone who has never owned them before, which means that he doesn't have a Jetton wallet. And in the standard of the Jetton, this is implemented in such a way that the one who sent coins also deploys the recipient's Jetton wallet. For this, we will pass the field code and init data. And in the end, we can send another replay message. This will be a notification for the sender that his coins have been sent. And actually, we are finished. This is, of course, a simplified version of the Jetton, but it's absolutely working. This Jetton is created by the same rules by which any other is created. A little later we will look at the standard, at how Jettons are developed according to the standard now, and now I just want to discuss the logic of the Jetton wallet again. I made a screen split here to visualize a little bit as if there are two separate Jetton wallets. And when we are sending a Jetton here, we get step 1. First of all, we check that our sender is the owner of this wallet. Then we check that we have enough balance to send these coins. And in case the check's passed, we subtract our balance. And then we form a message called internal add and send it to the one whose balance should increase. That is, we send a message to another contract with the same code. We get here and increase the balance of the contract. These are the principles on which the Jetton standard on the blockchain work. Let's now, in order to finish with the Jetton, I'll move on to our Jetton master and I'll write two more getters here. The first getter is to get the wallet address. and the second getter to get metadata from the Jetton, that is its symbol and the total supply. For this I use the metadata structure. Let's create a method here that will contain a symbol in a string format and total supply. And to finish, I'll compile all this now to make sure I haven't made any mistakes anywhere, and if I did, then I'll correct them. Let's start with Jetton master. I have a typo here. I indicated const here, but I had to use let. Another typo. And almost everywhere I have a typo with contract address. My require here also expects a second argument. Well, let's name it in case of an error. Let's move on. The errors don't end. Looking at line 36. I forgot to indicate that this is my cell. Yes, there are many errors. Now we will figure it all out. This is, by the way, very good that errors are occurring here now. So if you run into them, you will understand faster what is happening. I have a typo origin, and again, I didn't specify here that it's a cell. Hooray, finally compiled. This is another proof that Takt is, of course, a very young language, because there are not yet all these checks before compilation. That is, I can see errors only during the compilation process, not immediately during the coding process. Okay, and let's build the second Jetton wallet, and here everything is also successful. And before we close the topic with the Jetton, let's look at the code of how it is written in the library. I've already prepared this in advance. Here we have a contract, or rather trade Jetton, token, and Jetton default wallet. We also have a message. We have a list of them here. As we can see, the ID of this message is additionally passed in brackets. As I mentioned in previous videos, every message has an ID, and we can pass it manually here. We can put any number here, which will be the identifier of this message. And we can see here such messages as token transfer internal and others. There's also token notification, token burn, burn notification, and so on. Looking at the code. First of all, we see the total supply field here as well, and we see the mintable flag, meaning will this Jetton be able to mint new coins. We also have the owner's address and content. The cell is located in the content. We will talk about it a little later. The first receive method just the content contains everything related to the Jetton. Names, images, and other things. Let's talk about it a little later. Here we also see a second receive for notification of coin burning, and here is how it's implemented. That is, it's subtracted from the total supply. There are also getters to get the Jetton default wallet address, getter to get Jetton data. Here we return a structure in which the total supply, mintable, owner address, content, and wallet code. The wallet code is the code of our Jetton default wallet. Then we also have mint with the method we are already familiar with. Let's take a closer look at the Jetton default wallet code. Here is our first token transfer. As we see, it works by the same rules. Meaning we check if our sender is the owner, then we subtract the balance, and below we form the message, specifically token transfer internal, which will go to the recipient's wallet. We have additional fields here. We will not focus on this now. Let's look at receiving the token transfer internal message. And here it's also there. The first check is that if the sender is not the master. If it's not, mean it happening. Then we check if the address of our sender is correct. The logic of sending the ton coins is also written at the end. There is a notification that the coins have been delivered and also the sending of the remaining part. In fact, to get more familiar with the Jetton standard, I can recommend two more resources. The first is an article where all these patterns are explained, where we have parent and children, and each case is analyzed in detail. Here's an example of regular transfer case. There are other cases as well, for example with transfer notification. Here's another example of how the burn chain of messages works, which is the burning of coins. Let's parallelly look at this in the code. Here we have received token burn. After checks, first we subtract the reminder from ourselves, and then we form a message token burn notification. Let's take a look. Yes, at first burn came to Alice Jetton wallet, then Alice formed a burn notification and sent this message to the master address. Here we have a master called Jetton minter. In our code it's just a master. And when we receive such a notification, which tells us that we have to subtract a specified amount from the total supply. So we can look at other cases and scenarios. Here are many different references to this article. I will attach it in the description of this video. Also, be free to write comments to this video. I will be answering incoming questions. Lastly, about the Jetton, before concluding this lesson, I'll say a few more words about the content and in general just about the Jetton standard. To familiarize yourself with the standard, there is also a link to GitHub, which will be in the description too, in which it's described in detail what the standard should be, what requests, fields should be there, what messages, methods, and what is also very important is the get method. This is called get Jetton data. It is located in the master contract, get Jetton data. The structure of the returned data should necessarily be in accordance with the standard. This is to ensure that other services that will work with your Jetton. It can be exchanges, trading platforms, or whatever interact with your Jetton in the same way as everyone else. Therefore, get Jetton data should return the same data format for each Jetton. We see that there is total supply, we see mintable, admin address, and we see Jetton wallet code, which is a cell. At the beginning of the lesson I said that I would explain it a bit later. Now the time has come. In fact, the token content also has a standard, and in this standard we can look at how the content should be look exactly. I scroll down and see that there are fields like URI, name. Each of them have their own fields, their own encoding is specified. Thanks to this, we know what the fields should be and what the values should be, so that any dApp on ton will understand our Jetton. And as we can see, there is also documentation of NFT data here. And in the next tutorial, we will learn how NFT works. Phew, guys, it's been a long lesson. Thank you for your attention. We are coming to the end of our course. We have one lesson left on NFT, and the last 10 lesson will be focused on creating your own full-fledged dApp on Ton blockchain with its own smart contract, interacted with Telegram Messenger and Ton cryptocurrency wallet, and we will cover all this in the last lesson, after the lesson on NFT. That's all for today. Thank you for your attention. Goodbye.